Let me just share my screen. I'm audible, right?
Yes.
Yeah. Can you see my screen?
Yes. Yes.
क्या हुआ?
हाँ, visible है.
Yeah. I'll start. So hello everyone and a warm welcome to this really exciting session, which is based on the concept of distance ladder. I mean, it's a pretty weird name if you think about it. Distance ladder. What does this term mean? So, distance ladder is basically understanding the measurement of distances. And we will be using certain method called CFIDs, and this is really exciting because we'll get to get some hands-on experience with code in this session too. So that is something to look forward to. So yeah, we'll just be looking at analyzing distances and also learn more about this CFID method in this module. So again, why? So let's start with the most basic question, which is here. Why is the measurement of distances such an important topic in astronomy? So, I mean, let's just look at a real life example. If you want to measure maybe your height, you'll just use a meter scale or maybe like one of those tapes you get at the doctor's office. But if you actually want to measure a distance between two cities, you'll obviously have to use various other methods like GPS or airplane navigation or something like that. So that this is the difference, obviously. So you can't basically just use a ruler to find out the distance between two cities. So that is why you need different methods to find out different distances between astronomical objects in space. So this is where the concept of distance ladder comes in. So let's just go ahead. Yeah. So yeah, again, why go through this all this trouble to measure distance? Yeah, the measurement of distance is one of the most important fundamental properties of any planetary object. To if we need to know the distance to guess and estimate a lot of physical quantities like the Hubble's constant or or maybe some other properties which we'll see in the future slides. And also there's a lot of intrinsic properties of stars which are very important to us, like the luminosity, diameter, even the age of the star, which we can figure out just by knowing the distance. So basically, a complete study about astronomical systems is impossible without knowing the distance to the stars. So this is why distance is a very important aspect when it comes to astronomy, which because it is very important to measure distance to find out all these basic properties of a star, which is just fundamental to their existence. So before we move to the next slide, let's just recap on this very basic method of finding distances between two stars. This is the parallax method. I don't think I have to elaborate too much on this method because the parallax method is basically covered in the other basic modules, and uh, also one of the most basic methods found to measure distances. So yeah, the parallax method, just as a recap, uses the rotation and revolution of the earth to find out the angle subtended by the star after a particular period of time, to measure the distance by using simple trigonometry. Say this is the sun, this is the earth. It's going to revolve in like half a year, and it is going to subtend different angles to the same star in half the year. And to find out the distance, you can use simple trigonometry, just sine theta, cos theta, to figure out the distance between earth and the star. So this is what the parallax method is. But the thing what parallax method is, it is only useful for stars which have a distance of about 100 parsecs or about 300 light years. After that, parallax method is not right. It does not give you very accurate results of the distance, is what we figured out. This is because of a lot of different effects, a lot of gravitational lensing and all of those effects which we'll not get into. But yeah, this is the main reason that the parallax method is not viable for long distances. That's why scientists had to come up with a new method, which is called, and this is called the CFID method. Just for comparison, with the CFID method, you can find out distances to almost like 100,000 light years, which is like 300 times more than what you could just using parallax. So that's no, 3,000. I'm sorry. So that's why CFID method is was revolutionary. So Arash, he will tell you more about Cepheid method, but before that, I'll just give you a brief of what the Cepheid method is. So basically, let's start with what Cephids are. That is the first question you have to ask yourself when you're discussing the Cephid method. So basically, Cephids are these stars which are pretty unstable. So basically, there's a gas expansion and there's pressure differences which cause the stars to expand and then contract. And this expansion and contraction of stars basically causes a difference in the luminosity of the stars. And this difference in the luminosity of stars is very periodic, is what scientists had observed. So these are Cepheids, basically stars with a periodic luminosity which scientists have observed. So this is what Cepheids are, and yeah, so this method is used to measure distances to a galaxy and other astronomical objects, and yeah, to find out the distance to these galaxies, we'll need to use the distance modulus formula. I mean, we know what Cepheids are, but to find out the distance between Earth and the Cepheids, we need to use the distance modulus formula. The distance modulus formula is given here, and it will be derived in the future slides. But your m, just a sec, yeah, the d is the distance, m is the absolute magnitude, m is the apparent magnitude. So I'll just go in the brief about how we get m, the large m and the small m. So the small m is the apparent magnitude. It is the actual magnitude divided by 4 pi x square, because that is the magnitude we see on Earth. So we need to find out the x, or the distance between us and the Earth. And m, the absolute magnitude, is something which this scientist called Henrietta Leavitt, she discovered this. So she basically discovered that Cepheids actually are direct the distance between stars with this periodic luminosity is a linear equation in terms of the logarithm of the distance. So basically, you can write this big M as alpha into log distance plus beta, where alpha and beta are just two numbers. So this is what she discovered based on a lot of observations. So this will all get cleared up in the future slides, but she discovered a linear relationship between the logarithm of distance and the absolute magnitude. And using that, she and using and if you find out big M, you have all the other variables to find out log D. So this is just the basics about Cepheids. I'm pretty sure this was a little overwhelming at first, but Arash will just clear it up in the next slides. So yeah, I think I'll hand over the my screen to Arash. Yeah.
Hello, can everyone hear me? Am I
Yeah, we
audible?
can. Yeah,
Yeah.
yeah, you are.
Arnav just told you about the distance modulus formula. This was derived by Henriette Leavitt, and she was a famous astrophysicist. Uh, Wait a minute, I'll just share my screen now. Arnav, yeah, fine. So yes,
You're mute. You're mute, Arash.
we'll just take a deviation from this topic. We were discussing distance modulus formula. We'll eventually get to how we find out absolute magnitude and apparent magnitude, but first we'll need to discuss how this formula was derived. We'll do just a quick little derivation for the distance modulus formula. For that, first we'll need to know what luminosity is. I guess you must have read about this in the previous modules. It's basically it's synonymous with radiated power. The energy radiated by an object through radiation, electromagnetic radiation per unit time is referred to as its luminosity. This is required because the apparent magnitude, it's a measurement of brightness, and by measurement of brightness is proportional to luminosity. So it becomes a measure of the luminosity of the astronomical object. Now this is not like this was a made up scale. Like this was not derived. This is a made up scale, and this was an inverse logarithmic scale. So don't get confused. If the number of apparent magnitude is in negative, it means it's more bright. So keep that in mind, because you'll find the more brighter objects have an apparent magnitude that are negative. We get the formula. The constant is 2.5. This was derived by Leviata. Here M ref refers to the and F ref. Just a minute. Yeah. Okay. I guess there was some mistake with the image. Image should have been a little up. It's fine. I'll just tell you what it is. The MREF refers to the apparent magnitude of a reference object. Because there will be objects in star, you'll know the apparent magnitude of the objects closer to Earth in our galaxy. As the star Vega has been used quite a lot as an F reference, because it was used for quite a while back and that has stayed as it is. Here, F refers to the flux. Now, flux is just luminosity divided by 4 pi r square. Now, what I mean by 4 pi r square is the luminosity covered over the whole of the area across the which energy has radiated. Inverse distance law is used here. You have read about flux in your JE days, so it's basically the same. Uh, I'll just continue. Yeah. In the last slide, the Z was basically M1 is equals to M ref. So M ref becomes a constant, as we know the apparent magnitude. It's apparent magnitude, right, from Earth. And the law 2.5 log F ref also becomes constant. So it essentially becomes a constant Z plus the apparent magnitude. Yeah. So yeah, I have just covered what flux is in this next point. Now we get to absolute magnitude, the capital M. Now, why is that required? As you see, as distance varies, as you know, the brightness or how we perceive the brightness of the object changes as the amount of flux that we get into our eyes decreases. Uh, Absolute magnitude refers to the, as by the term absolute, it refers to the magnitude of object fixed from a distance. And we have defined that distance to be 10 parsecs. Now, parsecs is a distance unit which we might have covered while studying about parallax method. Uh, I will not go into details how it was. It's basically 1 parsec equals to 3.26 light years. The distance of 10 parsecs was chosen for the absolute magnitude. This again comes the Z part that I discussed on the last page. Absolute magnitude and the flux here becomes D equals to 10 parsecs. And yeah, I again discussed about luminosity. Uh, 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 Basically, I'm just discussing here how the flux changes as distance changes. Now, all these things, when you put together, these form the distance modulus formula. You remove the z that's subtracted, and you put the flux formula as the flux equals to L by 4 pi r square, and as the r changes to 10, you can just put those formulas, and at the end you'll get the distance modulus formula that was 2 slides earlier. Um, Now, yes, as we have now covered what the distance modulus formula is, I'll proceed further. Now, in the distance modulus formula, there was the term was m minus capital M equals to log 5 minus 5, right? Log of distance, 5 or log distance minus 5. Now, we need to find the distance. So, we'll first need to find the absolute magnitude and apparent magnitude of a C feed. Of a C feed, because why are we using C feed here? Now that's also a question, because why are we not using any other star? Well, that's because to find the absolute magnitude of a star that's not variable is very difficult. And how do we find uh, the absolute magnitude of a Cepheid? That's using period luminosity relation. This was also given by Levita. Here's the formula. The absolute magnitude is proportional to the log base 10 of the time period of the pulsation plus a constant beta. Now this was derived by Levita, and this was a groundbreaking discovery, as now we could measure distances much farther than the distance of our galaxy. We were able to figure out how far these stars were. Now, the period is of the period of the luminosity. We measure the apparent magnitude. The apparent magnitude can be measured through photometry. Photometry is a whole other topic. It will be one of your modules, I think. It's basically the technique to measure how bright a certain point in the sky is. You give it an exposure time. Photons keep hitting it. As more photons hit in a particular time, that means it's more bright. And you keep measuring this over a period of time, you'll get uh, a variable graph. As the brightness increases, it decreases, increases and decreases. Arnav discussed it, why it increases and decreases. That's because as stars expand, the outer layer, they contract. As the outer layer contract, uh, they come together, and because as they come together, they again heat up and they expand again the outer layer. That's where the time period comes from. If it was not clear earlier, I'll proceed further. Yeah. So how do we calculate alpha and beta? I'm sure most of you are familiar with this. We did a lot of linear regression last year. Yeah. So linear regression will be used here. But how do we get the data for the time period is the question. We know how to measure the the apparent magnitude. We'll see who helps us to measure that. So yeah, how do we calculate alpha and beta? This is where Gaia comes in. So Gaia was a telescope which was launched in the 2000s, which has helped us gain massive data about our galaxy. Massive amounts. It has really helped us. So we'll see how the Gaia helps us figuring out this data. So that's a red tinted image of data. It looks cool. I think, at least I think so. That's why I put it in the slide. So yeah, what's the data that Gaia gives us? First of all, apparent magnitude. I just discussed this. We use photometry techniques, CCDs, charge coupled devices, and others. These are semiconductor devices which are used to measure the brightness or the luminosity of an object through apparent magnitude. As we've just figured out luminosity, once we know luminosity, we can figure out the apparent magnitude. Now, the important thing here is that it gives us the apparent magnitude of Cepheids in our galaxy. Now, why is that important? We'll just figure it out. Let's just first see the next point. Parallax. So yes, this is the important bit. As Gaia measures the data about Cepheids in our galaxy. Now, our galaxy is about 10 raised to power 5 light years wide. So, in this diameter, parallax method can be used efficiently within a margin of error. I know Arnav just told us about that. It's mostly till thousands of light meter to give accurate, but even in 10 raised to power 5, it gives us within a margin of error that we can use this to create a model. Now, how will we create a model? As it measures the distance, we know what's the distance modulus formula. It's m minus 5 equals to 5 log log of distance minus 5. Now, with the help of parallax method, we'll get data about the distance. As we get data about the distance, now we have two variables, m and capital M. It also measures the apparent magnitude, as we just discussed. So now we only have one variable, capital M. So we'll be able to figure out the absolute magnitude of the Cepheids in our galaxy because of this, using the distance modulus formula. Now, why is this important? As we figure out the absolute magnitude, if you go in the previous slide, we can use the period luminosity relation. Capital M equals to alpha of log of base 10 time period plus beta. We'll know the time period as it gives us. It records M at various time intervals to find the time period. So we have the time period. Now we have the absolute magnitude as well. So we'll be finally able to figure out what alpha and beta is with the help of linear regression. And I will tell you in more detail about this after this, of how it is done. So once we have figured out alpha and beta, right? Once we have those figured out, we have a model of these stars. What happened? Oh, it's going back. So yeah. Once we have it figured out, the model, we'll have alpha and beta figured out, that we will have a rough model. If you have more data, you have a more refined model about how CFIDs behave with their time period, have a and have you have a linear relation of it with its absolute magnitude. Now we have a relation. So we can go and figure out about distance of galaxies much further than our galaxy, because now we have a model which we can use to find the absolute magnitude of CFIDs outside our galaxy. Arnav will tell you in more detail about this just a minute. I'll just discuss what Hubble provides us, because it provides us with CFIDs data, yeah, apparent magnitude of CFIDs in galaxies in our cluster. So yeah, CFID method is, as you will study in the module, it also has a limit, right? As you see, we have created a rough model almost, as you can't use this for distance farther than our cluster system, because the data becomes more vague and vague. There are other methods, the type LA supernova method. This is the surface brightness fluctuation method, which we'll read about in the module. But we are discussing this as this method gives a broad overview of all the things, because all these things are essentially used. So yeah, the other thing it provides us the time period, quite similar to Gaia. So I think, yeah, this is Jan, right? Yep. So I'll handle over to Arnav. He'll discuss with you a code. Now we have all this data. So how do we interpret this data? He has a Jupyter notebook which will tell you how he interprets this data and finds the distance of galaxies in our cluster at the end. So I'll hand it over to Arnav.
Yes, thanks Arash for that explanation. So yeah, I'll take it from here. So basically, we have compiled a code which will help us to process the data. As we see the code, you will probably see it better. So yeah, here's the code. I hope my screen is visible. Yeah.
Yep. Yes, it is.
Yeah. So basically, as I'll just reiterate, the code is to develop a model. We need to find an alpha and beta, and after we find the alpha and beta, we need to find the distances and see and just interpret the data. So how will you find the alpha and beta? So let's just run through the code. So initially, the first bit is just importing the necessary libraries, and the second part is just reading the CSV file. Then we need to get a scatter plot of m and log base 10p, because as we saw that Leviathan discovered that m and log base 10p have a linear relationship, and after plotting the data which we are given by Gaia, we will find the value of alpha and beta by getting a best fitting line. And yeah, so let's just discuss the code. And yeah, of course, the absolute magnitude formula is just mentioned here. So I've just found out the distance, which is 1,000 by parallax, and the small m, which is given by the Gaia data. I've just put it in the equation, and then just made a best fittings, and then just made a scatter graph of the equation of the x-axis as log of 10 period and y-axis the absolute magnitude. And as you can see, the scattered data is pretty concentrated, but there's some outliers obviously. So as you can see here, and then you have to make a best fitting line. The code does it all for you. And yeah, so I made a best fitting line, and afterwards the best fitting line, the code has given the values of alpha and beta as minus 1.75 and 0.45, which we will take. So basically, now that we have alpha and beta, we can find out we can find out the big M of basically any star which we know. Because which we know the time period of, so we'll be able to find out the distance. We'll be able to find out the actual magnitude of any star we want. So now that we have gotten alpha and beta, let's just also run through the code of finding the actual data. So again, this one more CSV file of the C feeds of the galaxy distances. So yeah, again, I have just run a loop for I in the length of the CFIT data, and this calculates the distance of the galaxy using the formula which we discussed before, and then just rearrange that to get a value of distance, which is 10 raised to m minus m plus 5 by 5. This is rearranging. So yeah, then afterwards, after you find out the distance, you append the calculated distance to the distances list. It's just simple Python programming, which is just like you found out the distance by using this formula and just added it. And then after you add it, uh, the remaining code is just to make a histogram of it so that you'll be able to see it. And but there is and one more aspect to it which we had discussed above. Some of the data might be inaccurate, so there might be some outliers which lie. So the outliers are just probably outliers, as you see, is like distances which are less than which are like really large, and which basically can't be feasible in real life data. So it's just basically maybe wrong data, error of measurement, and maybe something like that, but basically wrong data. I mean distances which are abnormally large. So there's also just a foolproof safe, so that the outliers are excluded. So basically after you all do all of this, you get this really nice histogram of the galaxy data, where you get the distance in parsecs, and you also get the frequency, the number of galaxies at that parsecs. So basically, you took the data provided by Gaia of just the CFIDs, and after you took that data, you found out the individual distances, and then you plotted the plot then you plotted it. And also, from the data you find out that one of these galaxies has just a distance of like a really small distance of 2383 parsecs, and this is unfeasible physically, so that this might be an outlier. This is what we figured out through the code. So yeah, this was a basic idea of the code which we used to figure out. And just to give an idea of how important this code and this method is, this was actually one of the problems in KSP 5.0, which we recently conducted this year. So if you're ever interested in maybe pursuing one of the future KSPs, or if you actually solved KSP this time, you will know about how you wrote this code. So yeah, this is what. So this is why how this is how important it is. So we are mostly done with CFITs. There's some last remaining part theory which Arash will cover now. Yeah, over to Arash. I'll just change the slides.
So yeah, Arnav just discuss about the code. That was a problem for the Kritika Summer project this summer. A lot of people attempted it. There were different codes that were run through it. We gave you a basic idea of the code. There are many different other methods that are used. So yeah, now we have covered the CFID method. It is one of the most important methods to measure distances in the universe. But there are also other methods that, like we have discussed, parallax method for distances closer to us. Then comes CFID method. Then after that comes type LS supernova. Type LS supernova, if you haven't read, is like uh, uh, just wait a minute. There's someone at.
He'll be back in just a sec. Just yeah.
Am I audible?
Yeah, yeah, you are.
Yeah, I'm sorry, there's some connectivity issue from my wireless at the moment. I don't know what's happening. So as I was discussing about type LA supernova, it's a supernova which has like its maximum absolute magnitude is a constant for every type. So you can use that thing to in the distance modulus formula and other formulas to find the distance. The other method, surface brightness fluctuation, is it uses a lot of data analysis about pixels. And that has a lot of maths used in it. You can go into it further. That's like the last topic of our module. A lot of math is involved, so we are not discussing that right now. That would be outside our capabilities right now. Uh, so these are all methods that apply data that we have gotten from electromagnetic radiation. But there are also other forms of data available, as you can see on the screen. And as you know, this is a relatively recent study. We first found out about these waves in like 2016. These are gravitational waves. So when two very massive objects are in a binary system, as you can see in the screen, they go around each other very rapidly. And because of their huge mass, if you apply the laws of general relativity, the space is flat. So as they go around each other, they produce ripples and waves. As you can see on the screen, these are referred to as gravitational waves. So can we somehow use this data to find the distance to where they are? We'll see about that. Um, yep. So yeah, as I just said, are there any other means except electromagnetic radiation like light through which we can measure the distance to an object? Distance siren. The thing right now discussed is termed as distance siren. Why siren? Because these waves come like sound waves. So earlier was a distance light source. So we term this as distance siren. Why is it not going further? Just wait a minute. Yeah. In binary systems, yeah, I will just in binary systems, the in spiral phase is what is termed as when two binaries are circulating around each other and this starts coming closer because of gravitational interaction. Why? As they come closer, angular momentum should be conserved. So their velocity increases, MVR, as you all know. Uh, and they have to maintain that angular momentum. So why they come close to this is because of gravitational interaction. So and their velocity increases. As velocity increases, the ripples and the waves they increase. And as you see in an isolated binary system, isolated ideal binary, basically they no nebular matter, no gas matter, is just two systems. In that isolated system, the energy that will be emitted through the gravitational wave will come directly from the in spiral as they are coming closer to each other. Yeah, as I just mentioned, the decrease in orbital energy. Orbital energy is the energy they have that's maintaining their orbit. Now it's not being maintained, they're coming closer, it's collapsing. That collapse, the decrease in energy is all going through gravitational waves. Uh, Now this formula, this here, F is the frequency of the gravitational waves. They are essentially waves, the waves that we have studied from like class 9th. So it's a differential equation. Of course, it is, as all complex equations are. It's equal. Now this term is quite complex, why is there pi rich verb 8 by 3? We'll not go into derivation. We'll just go into the idea of it. What it's implying. As we see, the G, now there's a cursive M here. What's that? We'll discuss that. G is gravitational constant. F is the frequency. Now you see the change in frequency with time is dependent on frequency. That means if tells us is there is a collapse. As it comes closer, rate increases, as it comes closer, increases. So it's leading to a collapse, which results in like a kilonova explosion. I think I don't think it's termed kilonova. It's a very big explosion. C is the speed of light. So it basically the variables in these terms are m cursive m raised to power 5 by 3 and cursive f raised to power 11 by 3. F is the frequency. What's cursive m? So here we see cursive m is called chirp mass. This term is very important when talking about black holes and binary systems as a whole. It represents a quantity as it's written. That's a of the combined mass. Why combined mass? Because binary system really depends on the mass of the two objects. Uh, if you'll see, if the M1 is quite large and M2 is small, it can't, like, it will vary a lot. The chirp mass varies about system whether it ends up as a binary black hole, binary neutron star, whether it doesn't end up in a binary system, it just combines before, whether it just falls apart. There are a lot of things that happens to binary system. Like again, this was a topic for a KSP project, uh, binary systems and how they expand about in terms of initial systems. Chirp mass is a hugely important factor because of that. Now, this also varies in its timeline. Initially, it will be quite large, but mass losses happen due to like supernovas, masses scatters, mass transfer also happens. There's a lot that goes on here. It's a really complex topic. Me personally, I have been doing a KSP project in this for 2 months. Even I don't completely understand it. Like I can't make you understand it in half an hour. If you really want to study, there are a lot of interesting articles about it. I think in a week or two, we will have reports about this particular topic as well. If you really want to discuss further. Basically, it's telling us how the frequency is now. The main how do we measure the distance of that thing? Really went on a tangent there. So yeah, if we absorb the waveform, you know the frequency of it. Now, you know the power that you are receiving through these waves. Computing the Chern mass, the power of waves can be found out from these waves, and it was termed standard science, as I just told you. And that you used to find the distance following the inverse square law. This is quite similar to the Seyfert thing. The whole flux thing, flux follows the inverse square law. As the distance increases, the flux follows the inverse square law and it decreases. Arnav, are you saying something?
Oh, I'm sorry. I'm sorry.
Okay, fine,
Let me
fine.
yeah.
No, no. The slide went away now. Just give us a minute. Yeah, yeah. So we are back. Uh, as we just discussed, flux follows the inverse square law. So you can use the whole derivation that we used in the distance modulus and the periodic luminosity, the whole thing that Leviata followed. And now we have the power, the frequency. So we'll, as we know the power, we can, that can be synonymous to the apparent magnitude and the absolute magnitude, which was the whole luminosity thing that was essentially power radiated. This is essentially the same. So these terms can be converted to the distance. If you understand what I'm saying, you can ask doubts later. Uh, Essentially the same concept. That's why we discuss Seyfert method in such detail. Uh, Now, as we discuss in Seyfert method as well, there are problems with the system. Hence, we can't use them for distance greater than like 10 power 7 light years. Now, what are these problems? Gravitational lensing is one of them. This is another very interesting topic. A lot of research is going on this currently. There was like, let me just first explain this. Uh, as if there, as you see the diagram, Earth is there. We see light traveling out from quasar. Quasar is like a neutron star of a specific type. We'll not discuss that here. Essentially, it's radiating light. That's all you need to know right now. Now, there's a galaxy that's right between that quasar and Earth, as in the diagram. That the light, the photons that will be traveling alongside that galaxy will be attracted to that galaxy, as we see in the diagram. So, the path of light curves, as we see around the galaxy. This is what we observe in the photos of black holes. The whole ring that we observe around it, that's light bending from black hole, right? The accretion disk, it's bending. That's a whole other topic, but basically the light's bending around the galaxy. Now, as we have seen in optics, when light bends, we perceive it coming from the direction that it hits us. So from Earth, we perceive it as hitting us. As you see in the diagram, if you can see my mouse, here it deviates and like it goes on a completely different direction than from where the light has come. Now you can apply trigonometry here. This distance that we perceive is way higher than what actually it is. So this is an error of a large magnitude. And we also see that the light from the same star, we perceive it in other directions. Like you can see 4 here. So as I was discussing recently, like I think in the past 10 years, there was one supernova. I don't remember which date, which we saw at 4 different instances. So how that was due to gravitational lensing. So as you can see, there are 4 stars that we are seeing. We see these as coming at different intervals of time with different intensity, but we are seeing the same thing. So that's like a really interesting topic. If you need to deep dive, you can read about it further. But the thing is that we need to discuss that the error that we get from resulting from this is quite large. That's not recoverable data. Oh, so now we come to weak lensing. Now, weak lensing is the same as gravitational lensing, just instead of a galaxy, like there's a star, and there are multiple stars in your line of sight. Here's your main star, here's the Earth. There will be a lot of major masses between them, which will bend light. Now, they won't bend light as much as a galaxy would, but they will bend light, and there will be multiple instances of it. So you can't figure out if the data you get is correct. Now, what the image we are seeing, it consists of neutron stars, as we just discussed. This merger is what we get a kilonova slash supernova explosion. This is another method. Once we get this supernova kilonova explosion, as is quite similar with supernova type 1A, which was studied, we are of a specific magnitude of brightness fixed, and you can use that to find the distance. Now, why is it fixed? That's a whole other topic that evolves how stars evolve over time. Uh, why their brightness is same is complex. We can't really discuss it here, but it's essentially how stars evolve, and its dependence on its mass, the distance between these stars. So yeah, this is just another method like supernova type A, which can be used to find the distance. Okay, so we'll run through this a bit. This isn't really for example, like you need to know the scale of things. You need to know how much your copy measures. The measure of the copy, you need a scale for it, like a steel scale. You can't really measure it without it. So standard rulers are objects in the astronomical sky which can be used as a scale to measure things aside it. Like, for example, your friend is standing at a distance. If there is a pole beside it from of which you know the distance of, you can measure the height of your friend, approximately at least. Uh, that's a way to find the approximate distance. Like it's a comparative show. It won't give you exactly what the distance is, but this is also a method you should know about. Like, can I get the next slide? Yeah. Yeah. So what can be used as scales? Like these are very different things. Now, a object can be classified as standard ruler. Standard ruler as what is a scale, which can be used as a standard, like vernier calipers, which we use. These can be used as standards. That we can determine the size of things aside it, right? So, what are the objects? Can I go back to the previous slide? I'm going to the next slide.
I'm not doing anything. I don't know. Just a
Okay,
second.
fine, fine. एक बार जाएगा या पिछली स्लाइड में मेरे से नहीं हो रहा. Yep, sorry about that. We were discussing what objects can be used as a ruler. Back in 2008, like this is relatively new study. Galaxies were proposed, like galaxies, the study of galaxies very different because galaxies are rotating. So you'll see things bright, revolving. So that's also periodic way. Periodic relation can be used of it to measure things. uh, we're not going into the detail of it. I am just telling you, it's similar to what we do. They were proposed as a possible standard ruler. But recent studies about BAO, baryon acoustic oscillation, has been proposed. Now, this implies science about cosmic microwave background radiation, as we have seen. This goes back to the Big Bang. Now, how is Big Bang related to measuring distances of scales right now? We'll see that. Uh, in the very early universe, like the baryonic matter, that's protons, electrons, the density of those was variable. As you see, the temperature creates a lot of variation in the density of matter, and that density uh, is what we use. Now, how do we use that? As I see in the primordial plasma of the early universe, there was baryonic matter, and there were density waves that were created because of the variable density. Now, so yeah, in the early universe, as the baryons and photons scatter off each other, like they hit and they scatter off each other. Before recombination is when electrons and protons come together to form atoms. So that was before recombination. So early universe, they form a tightly coupled fluid. Now, what's coupled fluid? Coupled fluid is fluid formed observe the coupling of electrons and photons. That they have not joined, but they have formed a couple because of their interaction. Now, because of these waves and their hitting of each other, some areas become more dense and some areas become less dense. This was variable until recombination. Now, what happened? As I have written, the waves are sourced by primordial density perturbations, density perturbations, disturbances in the primordial matter, and the density waves are created. And they travel at speeds that can be predicted from the baryon density. Now, this is not really required. What's happened is the total distance of these waves that can travel before recombination determines. Now, these waves are formed because of density. Now, these waves, they travel a distance. Now, when recombination happen, it's like the distance they traveled at frozen time, because you can measure that wave. Because now this is, I'm just telling you the gist of it. You need to go more deep into this because primordial waves, these are all complex topics that require a lot of maths. I'm just basically telling you density perturbations created waves waves traveled according to baryon density before recombination. That is, matter flows there. The total distance they traveled, that's now able to measure, uh, because when recombination happened, it become fixed, and after that, space expanded. So it's like a rubber band. That rubber band is fixed. You just are expanding the space, so it's getting bigger. So you just need to know how small the space was, and when the waves traveled, you can use that distance of the waves as a scale of very large scale to measure things. This is a complex topic. I understand if you don't understand it. I personally also don't completely understand it. You need a lot of maths for this. I just wanted to convey that this is also a method. Density perturbations in the very early universe can be used to measure things of large scales today. Like, that's really brilliant according to me. I just we wanted to share that these things are happening currently. So yeah, the history of the universe is mentioned. Uh, I gave this diagram just to give you an idea of what part of universe we were discussing. It was the early universe before the first light and the first nuclei, between this time period. So I think that's it. We have discussed most of the methods used to measure distances of galaxies and objects far away from the Earth. Uh,
Yeah, do you guys have any questions? If yes, we can answer them now.
yes, we can take questions now. It has been a long session. I think one of your longest sessions so far. This is required because without measuring distance, you can't really do any other science. Like, this is the
Yeah,
basic. Like,
exactly.
in 11th you study calculus. Without that, you can't do your JEE prep, right? If you don't really study distance ladder, you can't really study about other things really, uh, without having this is the basic thing if you really want to pursue things further. So yeah,
Yeah,
feel free to
but
ask any questions.
I guess not. But yeah, if you have any question, just tag us or just tell us on Teams. We'll be ready to answer. But yeah, thank you for staying patient with us in this session, and I hope you had fun and learned something new. And yeah, just if you have anything, just let us know. I guess we can take a leave. Yeah.
Yeah, you can ask any other questions. Like, I discussed a lot of other things that were not really relevant. You can ask for any other articles because I studied those during this time period. So yeah, feel free to DM me in case. I guess all
Yeah.
of you most have my number as well.
Jigyasa, can you tell the next schedule? I guess we'll just finish with that.
Yeah, so we're done with two advanced modules sessions for now, and we've also uploaded another two in the past 2 days. We'll be having more sessions for the advanced modules because they're more in numbers, so these are quite frequent. And I know it's a little inconvenient, but I mean, you just gotta do 4 out of the 7 modules that we're going to have. Next module presentation is probably going to be exoplanet, and the presentation is going to be tomorrow. The exact timings will be posted by tonight, hopefully. And yeah, I hope everybody understood today's session. And again, a gentle reminder that please keep reading the modules, and these sessions are just a introduction to all these concepts that you'll get to learn in the modules, which are very well better explained there. So I hope you had fun. Okay, then, in case of no doubts, I think we shall end the meeting here. Thank you, everybody, for joining.
Thank you, everyone.